Hello everyone, this is Mr. Nadj. I am going to share with you today what to do with motion maps. So the subject of this uh, video is to make sense of motion maps or motion diagrams. These are the two words that people usually uh, would refer to them, diagrams, okay? Now, I already have a motion diagramming map. Now, of course, you already kind of worked with motion maps or motion diagrams yourself when you did the constant velocity particle model lab, when you recorded the video and then you set your dots at equal, either frames or multiple of frames. And in doing so, you already kind of worked with motion maps. But they are a lot more useful than that than you may think. So here's the deal. I already copied a motion map. I'm going to paste it in here, and I'm going to bring it, down here, and I'm going to make it a little bit big so it would be easy for you to see and follow me all along. Okay, so here we go. I hope this is big enough and it can be seen well. Very good. The other thing to keep in mind is that our textbook author is really cool in the sense that he has a specific deal that is very cool. What he does is anything that is related to position, like X, Y, things like that, he would represent it in blue. Anything that is related to velocity, like V sub X, V sub Y, things like that, any V type of stuff, velocity stuff, he represents it in green. And then anything involving the acceleration, A sub X, A sub Y, etc., he would represent it in red. So in this case, you see that the motion map is represented by green vectors or green arrows, okay? That means it's a representation of the velocity. The most important feature about of motion maps or motion diagrams is the fact that the going from dot to dot, you are going equal amounts of time. So for example, when you did the constant velocity particle model, the spacing of these was the same, and they were representing 5 frames at a time or 10 frames at a time, depending on how you set yours. This one is also the same thing. So from dot to dot, it's equal amount of time, like for example, 1 second. We're gonna go with that just for the sake of, to make it easy. So that means this is an initial velocity, this is a future velocity. Or this is an initial velocity, this is a future velocity. Or this is an initial velocity, this is a much future velocity. So all of these, are representing the initial velocity and some subsequent velocities beyond that. Notice here how the velocity vectors, here are maintained the same, okay? If you look carefully, if you try to match it right here, you see that it is equivalent to about 5 squares. Here, on the other hand, if we try to match it, you see that it is 2, 4, 6, 8, 10, 12 squares, etc. So, in this case then, apparently this is showing a motion where an object is maintaining some speed, and then changing that speed, and then apparently maintaining that same speed all over again. So for example here, if I set this right there, and I put my finger right there, and I slide it, you'll see that I'm getting the same amount of spacing. I don't know if you can see, but apparently I am in the way here. So here we go, look at that. Look at that. So I'm going from center to center, and as you can see, this is the same. So how do you use this a little bit more effectively than just that? Well, first of all, if this is, for example, I'm just gonna use, let's say I label this as my VI. And I label this vector right here as my VF, meaning future velocity. I know the textbook and authors usually use V final. I don't like the word final. This is some future, one, because obviously it can't be final when there are so many other ones that are coming afterwards. So this is one of the future velocity vectors, okay? So if I take this vector right here and I place it right underneath the other one, I hope you would see that I am having a match in terms of length. Now, of course, these dots are not supposed to be this humongous. So technically, this is really my vector right there. So they're technically, right there. So I'm taking that and I'm putting it right here. And as you can see, it's matching. So if I draw this as being my initial, notice by comparing my initial and final, if I try to figure out the amount of change in velocity, okay, meaning my VF minus my VI, I am ending up VI, I don't know why I wrote F, but anyway, is equal to 0. Cool? Say cool. Now, if I take this one and this one right here, I hope you would see it's a different deal. So in this case, I am having a velocity vector right there. So let's say I label this one as my VI, okay? And this one as my VF. Notice here, I'm just, pretending that I'm starting right here, and I'm going this way. So let me bring this one and put it right there. I'm going to go with the length that they gave us here, even though I really don't like the fact that they said it, right after the dot right there. So it's roughly about this much for the VI. So notice here, this is my VI, this is my VF. So this is the amount of change from VI to the VF. And notice how the amount of change is occupied by this little space right there. Well, guess what? That is going to be representing the change in the velocity. Now you would say, wait a second, Nadj, why are you drawing that in red? Well, this is going to be related to the acceleration because the acceleration as we know it is supposed to be the change in the velocity over change in time, isn't it? And if this, earlier I said the delta t, we're going to take it to be equal to 1 second. So if this is equal to 1 second, then my delta v and my a are going to match. But still, this is my delta v. Now technically what you should do, you should take this here and you draw it above this, because in the transition between these two, I am having a vector that is this long, which is representing the acceleration. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is representing my acceleration. Cool or no cool? You may think, not cool yet. Because what if you have a situation where the vector gets smaller? Well, let's do a situation like that. So, how about I do this? Are you ready, my friends? So, let's say, for instance, I have something that starts off, let's say, like this. Let's say 2, 4, 6, 8, 10, 11. Oh, yes, love it. And then I go from there to, let's say, 2, 4, 6, 8, 9. And then we'll go 2, 4, 6, 7. I'm just trying to go with odd numbers so I would have a better chance of stumbling upon prime numbers. You know I love prime numbers. And then, let's say 2, 4, 6, no, silly Nadj, say silly Nadj. Okay, 2, 4, 5. So let's say I have a situation like this. Okay, so this is a motion diagram. And notice here, mine is much better than the other one in the sense that the dots are really small, so they are not interfering with this. So in this case, how would I go about figuring out, let's say, the amount of acceleration involved? Okay, so this is my VI, okay, and this here is my VF. Remember, you can select your VI anything you want, but once you set that, everything that comes after it, that's going to be some future velocity of some sort. No final, future, better. Okay, so in this case then, I'm going to take this vector right here, and I'm going to put it underneath the other one, so I would be able to compare my initial and my final one. So again, we said that this one is supposed to be 2, 4, 6, 8, and 1, 9. So 2, 4, 6, 8, and 1, 9. Now notice here how my VI here is overshooting my VF. So that means technically what happened to this is from going to VI to VF, I had the vector shrunk literally by a certain amount. By what's a certain amount? This amount right here. So it shrunk by this little tiny amount right there. Guess what? You would put that vector right on top of the transition point right there, and you say that this is representing the acceleration. Technically, this is the change in the velocity. But if you are considering the time change to be roughly about a second for each one of the, the points in your motion map,
then at that point, this is the acceleration. Notice how the acceleration vector here is pointing to the right. Cool or no cool? Now, of course, hopefully when we do some of the examples and exercises and you do some of the online homework, you'll be able to actually make sense of this a little bit more.
My friends, thank you very much. This is the Nadj signing off. Here we go, right there.
Yes.